The next block of talks will start with Kochunas, assistant professor at the nuclear engineering department. His research focuses on the next generation of numerical methods and power algorithms for high fidelity computational reactive physics. His areas of expertise include neutron transport, nuclear transmission, multi-physics, power programming, and matrix architectures. During his time as a PhD student, he initiated development of the AMPAC code that became the main deterministic neutronic instrument with the Castle program. And subsequently, their impact was not only born out of his PhD research, but has also become a central research tool in the work of more than 40 other PhD students in the nurse department. Bennett?
Yeah, thanks, Pancho. Welcome, everybody. Thanks for sticking around through talk number 3. And I see some current and former students from my class, which is good. But I'll be talking about a Catalyst grant that we've had for the past year, myself and Xinyu Wang. And recently, some of the other people actually contributing, doing the work, my former research scientist, Qishang Shen, current one, Suyang Choi, and then Xinyu's PhD students and postdocs. And then Yatin has also been helping us of late, but he was not a part of the original Catalyst. And so our Catalyst project was this performance-aware program synthesis for scientific computing. And I tried to come up with a provocative subtitle, which was, enabling effective. I think the call, my initial one was lazy, but I guess I'm being sort of disingenuous to students, naive, right? So we want naive programmers to be better programmers, right? More effective. All right, so what I'm going to talk about is, just give you an overview of what we're trying to do with this Catalyst grant. And a lot of this, next 30 minutes, I guess, will be about the problem and explaining that, and then kind of one idea for a solution. And sort of throughout all of that, I'm going to rely on the golden oldies here, matrix, multiply, sort of a concrete example to illustrate some of the things and give you evidence about what's important and what's not. All right, so our Catalyst grant, this is like an infographic for it, but if you're not familiar, program synthesis is just kind of like machine-generated code. So at this point, I think, if we're writing code at some point, we've probably all given a prompt to ChatGPT to basically write some code for us, right? So that's sort of one example that we might be familiar with for what program synthesis is. But you give an input and it produces an output program. And here what I'm saying, the input is, is really maybe some details about the hardware that your code is going to run on. And, my vision for this is, the other input is like just the mathematical algorithm. Like I can go read a paper from SciAm or look at something up in a textbook and, just write it out in its mathematical form. And what I want to get out of that is, high-level source code for that kernel or that algorithm that is really high performance. Okay, and then the synthesis is this middle part. And my clicker is, there we go, is this middle part. And there's lots of different algorithms and things you can put in here to generate that code, right? There's sketches with holes is the one that Xinyu has often mentioned, but you can search in trees if you have a sort of a finite solution space, and you can also use neural networks and large language models and other things. So it's kind of the wild west of what you put in the middle. So that's the big vision, right? That's where we want to end up. To get there, there's a few key challenges, like in a broad sense, but then there's other sort of more specific ones. In a broad sense, like the terminology here for what the input is, how you describe the problem to the synthesizer. So that's this middle part. Or what is the domain-specific language? Like, how are you going to express, here's the algorithm that I want? Is it going to be this mathematical form? Is it going to be other source code? Is it going to be some intermediate representation? That's a choice that you can make or you have to make, and it can evolve. The middle part is, I'll point out, to I think have success here, whatever the algorithm is, it has to be able to sort of rely on the 50 years plus of expert tricks that programmers in scientific computing have come up with to create good solutions for efficient programs. And the challenge there is like, how do we systematize that into some other algorithm? Okay, a few other key aspects, right? You want the synthesizer to do some verification, right? So it produces an output. You want that output to at first be correct. Like, we don't want to get broken code. I'm sure we can all write enough broken code ourselves. We don't need machines doing that for us as well. Okay, but then the other thing that's kind of new to program synthesis is this notion of like, we can have multiple correct solutions and they have a different quality, right? Some solutions are better than others. And so what is the quality that we're trying to measure in our synthesized program, and how do we do that? So our progress so far, again, we've been working at this for about 6 months. Collective learning, we've sort of mastered the example of matrix multiplication, but there's a very lengthy, again, 155-page review article that's 10 years old that sort of covers the full body of work of what we're trying to capture. Okay, so right, our main focus of late has been just making sure we really, really understand, have a deep knowing of what all these tricks are so that we can begin to systematize them. And so this is still a work in progress. The domain-specific language is still a great question of what this should be. Okay, and then some simple, I would say, engineered solutions for the other two things. Like, is the program correct? Well, at the very least, if we start with an input program, we can just check that they both produce the same solution. And then how to measure the quality, what we're doing here for now, and I'll talk about this, is just dynamic analysis. So we're instrumenting the code, measuring sort of the low-level operations that get executed to see if we're observing what we expect. And so later, possibly this could be done with like type of static analyzers, but I think there's probably a little bit of work to do there. So, right, my background's nuclear engineering. I only moonlight as someone in computer science. All right, so what's the problem? Like, I mentioned this review article, and if you caught the title, it talked about these communication avoiding algorithms. That's going to be kind of the theme here. And if we want, like, I'm going to walk through this very simply. We want high performance code. What does that mean, right? Ultimately, our metrics is minimize the execution time of our program. That's what we're after. But that's kind of opaque, right? We can't use that and sort of have some actionable plan of how we're going to do that. Like, what is it that determines our execution time? So the classical view is that it's just the time to perform your floating point operations. And I would say that this has been, as I see things in my world, this has been sort of stubbornly persistent as the classical views. There are still folks that think this way. Okay, but this stopped being true in the 90s. This is 30 years old. Now, the modern view is it's the time to perform your flops and the time to move data. We just heard it from our previous speaker. The bottleneck is moving data, and the solution that they're trying to come up with there is to not move the data, but just add hardware to the memory that's going to do the computation in memory. Me being more on the coding programming side, less on the hardware side, I want to figure out what the strategies are to deal with this. Okay, and so now I'm going to try to convince you that this is important. And for a naive programmer, there's some unintuitive results here. And here's where we introduce our matrix multiplication. Again, so we're thinking about time to perform flops versus time to move data. And my students in here will recognize this because it's part of their assignments. But we can write this as naively as 3 nested loops, which sort of naturally follows from how we think about it when we write it down mathematically. And we can run an experiment with different matrix sizes and just reorder these loops. All we're changing, we're just swapping I and K here. Very simple. Okay, and when we do that, what happens? Well, this is what happens. You get a range of times. So if you look across a row at one matrix size, you can see there are a range of runtimes here. And again, we didn't change the number of flops here at all. But what we're seeing is about a 20x difference in runtime. For someone who's kind of new to programming, think about your undergrads, your first year graduate students, this doesn't make any sense. And if you take a step back and think about like, well, why should this be the case in the first place? It seems kind of silly. There's good reasons for it, and we don't have time to get into them, but this is sort of the reality of the programmer. If you don't understand certain things, you might be running 20 times slower than you need to be. Okay, so clearly this term, the time we spend moving memory, is really, really important. We should be more focused on this than our flops. Okay, and also point out, like, I used optimizations here, and interestingly, with the GCC compiler, when you run with O3, it enables this option, F-loop interchange. What does that mean? Well, if you check the compiler documentation, it says for loops like this that look an awfully lot like matrix multiply, it'll change the order to give you better performance. That didn't happen here. So again, like, there are simple things. I can't tell you exactly why. I suspect that because I have flattened these arrays and they're not multidimensional. But there's, that's sort of, again, opaque to the programmer. These are details I think productive computational scientists don't want to have to become experts in. Okay, and the situation gets worse, of course, right? My best naive time here is still leaving about a factor of 25 in performance from, an expert solution. Okay, so again, like, this shouldn't be hard, and you might argue, well, we should just be using libraries, but I would say there's a host of other issues there that's not the best thing. You can think of a program synthesis solution as, rather than a library, and you're pre-compiling, installing, and understanding how to use a particular library. You're just sort of generating the pieces of the library that you need in your code on the fly. Okay, so again, this concept of communication avoidance, this is what we're focused on. We're going to minimize this term, and conceptually, moving data is what I'm calling communication. So we just want to do as little of this as possible with our implementation or our algorithm. All right, so what are some potential solutions there? We can put, hardware in the memory to prevent that. We can do, there's some other work I'm aware of going on where they're looking at sort of more advanced memory accelerators on the chip. So put it in the chip, not in the memory. But this paper I referenced at the beginning, so communication avoiding algorithms for numerical linear algebra, most of our key kernels are here. We know what the right answer is. They're non-trivial to implement, but this is pretty much all of your dense linear algebra that's really important. And then your Krylov solvers and things based on a sparse matrix vector multiplication are here. And then some other algorithms too. So DNNs, they have some, and fast multipole. And I'll say that, the level of analysis done here is they know what the absolute minimum amount of data is that you need to move to perform whatever the calculation is. So there's a lower bound. And then we know algorithms that achieve that, like there's a theoretical lower bound, and we have algorithms that achieve that. We know what those implementations are. But we don't know that for everything. There's still a good number of other types of calculations where we haven't studied these. They're typically more niche. All right, so, what are we trying to synthesize? What is the knowledge contained in, 10 to 20 years in a dozen PhDs of how to do this? That was considerable effort. And I can also point to, there's the recently completed major program in the Department of Energy, the Exascale Computing Project. It was basically like 40 to 50 science teams in computational science taking their algorithms that run fast on a CPU and figuring out how to make them run fast on a GPU. And that was like 10 years and $1 billion or something. So again, there's this wealth of information that has been generated, and how can we sort of extract from that the lessons learned to create an automated tool? Right, so can we incorporate the lessons and techniques in this previous work in our tool? And the other question we should ask is, like, is anybody else already working on this? And there are a few related efforts, and these are some of the ones we've compared to. So briefly, there's one called Kochunas, which is like a C++ library, and it attempts to abstract away the details of how the multidimensional arrays are laid out in memory. And then, gives you sort of some predefined schedules, meaning like order of operations or patterns of calculation. So like a for loop or a reduction operation. Another one from MIT, Halide. So again, a language for fast portable computations on images and tensors, allows more expressiveness of this concept of a schedule of, what your, again, you think of that as like order of operations of your calculation, for the compiler to do some additional optimizations on. Another, sort of one that I would say is rather popular is Taco, so the tensor algebra compiler, fast compiler-based library for sparse linear algebra and tensor algebra. It uses concepts of sort of iteration graphs to kind of optimize kernels across multiple possibly nested loops. Then another one, Legion, same idea of sort of scheduling, and it extends some of those to different hardware. Okay, so like how do they stack up? Come back to our matrix multiplication here. We'll start with the figure on the left. This is OpenBLAS in red, right? So this is our best known algorithm. This is the upper limit of what we can achieve. And the three other results here, so we have our hand optimized. So if we're an expert programmer who knows quite a bit of details, not a naive programmer, we can get about 50% of OpenBLAS relatively easily, I would say. But if you look at Halide, so it will auto schedule the operations for you, where you don't really know what it's doing. You just say, do your best job. And it doesn't get nearly that. And you can also, give it a lot more information. So if you have the same knowledge as the expert programmer who did the line in blue, and you express that information in Halide's kind of syntax, then you can do you can do better, but you're still at the same sort of asymptotic limit. Neither are doing as well as OpenBLAS. So we're still leaving like half of our performance on the table. On the other side, I'm just showing you, so this blue line becomes the orange line here. This is our expert coded one. And then Cocos, which I would have expected to do better, still isn't doing that great. So they sell us, for me, like I don't care about the research gains and neat CS stuff that's going on in these libraries. Like I just want fast code, right? And our students, they just want fast code with minimal effort, right? So there I'm saying I'm lazy. And they, Cocos has been going for 10 or 15 years and I'm sure has received significant investment. And if you pick it up, you try and use it off the shelf, you're better off with OpenBLAS, or if you know what you're doing, you'll just code it yourself. Okay, so like what's going on here? What does the expert have to do to get this line? So this is not our naive line. Our three nested loops line is like somewhere down here near zero. It's like one gigaflop or something. Okay, this is how that expert one works. You basically, so you do some blocking. You change your loop bounds here, right? That if you're familiar with performance optimization, blocking is kind of a common idea. And then you replace this inner loop with a kernel. And so I'm trying to illustrate down here what that looks like. You grab these blocks from your three matrices, and then you do the operations on them. And the other thing that is kind of non-intuitive when we think about this. So normally we think about a matrix multiply, we take this row of A, we multiply, we do dot product with this column, and that becomes the first element in here. Well, our kernel here, right, it's easy to imagine blocking and just doing that over the different blocks in the matrix, but our kernel here is going to sort of flip that on its head. It's going to, instead of, taking the row here, multiplying with the column here, it just takes the first element in our first row and column and scales the rest of the row in B by that amount, and you do the looping that way. And so this is the code for the kernel over here. Right, this innermost loop, J, that's kind of what I'm showing you here in green. Red is this part here. But you're also taking advantage of SIMD, right? So in this particular architecture, we have 512 bits, that's 8 doubles. So that's where this 8 comes from. This is just 512 bits and bytes. And then on this processor, so this is for Great Lakes, they have 2 floating point units, so we can do 2 of them at the same time. So with knowledge of our microarchitecture, we can choose some parameters of our kernel to say, all right, I can do basically 1 row of B here if I've made my kernel the right size in sort of 1 clock cycle. And then I can be efficient in my memory patterns instead of doing a row of this and a column of this. If I flip that and just do a scalar here and a row here, so my striding in memory is larger here than it is here. And that's basically it. Like, there's nothing special about this. There's no like handwritten assembly or anything else. It's just knowing that, oh, I just have to do this. Okay. And that gives us a lot of speed up, right? We're getting half of OpenBLOS, and this is essentially the code for it. But are we, I said we want to minimize communication. We want to minimize our data movement. Are we actually doing that? Okay, so I'll come back to that question in a minute. I just want to emphasize, to write the expert version, you have to know the details of the architecture and what all that means. You have to know the details of the memory layout of multidimensional arrays by the compiler. You have to know the effects and strategies of blocking, and you have to know how to do the change in order of operations for dot products and mapmul. That's a lot of information that we're asking computational scientists to know, right? They have to be experts in their own engineering discipline, and then they have to be experts in all this stuff to be productive. All right, and so that's why they take my class. And again, I want the goal of the synthesis tool is to make use of these concepts in a general way, like systematize them, put them into an algorithm and a program so that you don't need to learn all of this necessarily, right? High school students today just interact with smartphones where there's not really a representation of a file system, and they have no idea what a file system is. We can improve and keep building layers of abstraction here so that people can be more efficient in producing high performance code. All right, and then a couple other things I mentioned at the beginning, right? Additionally, we want the synthesizer to verify the solution. So we'll do things like check that the code compiles, that it gives the same answer. This is a simple solution for now, but what we might hear about next from Yatin is formal methods for doing this, as I understand it, maybe. Okay, and then, right, this other aspect of quality of solution, and this is where this is sort of new in program synthesis. Like you have a notion of quality of solution in here that refers to the performance. Okay, it's sort of well known. Compilers do not know about other algorithms. They don't, I guess in terms of linear solvers, right, you've got like a direct solver, you've got multi-grid sitting over here. They don't know that. Like, they just know the code you gave it. And then we saw from our earlier table on matrix multiplication, even if you know the mathematics and you don't know programming that well, you can still screw up by like a significant factor. Okay, so again, what we're after is how do we measure these things? And it's harder than you think, but we want to be able to measure the time to move data and the time spent moving data. All right, and I said, like, our initial thing here is we're going to do dynamic performance measurement, meaning we're going to run the output code and measure how many operations it's doing, right? So what can we measure? Our measurement sort of infrastructure here, there's a library from Jack Dongara at UTK called PAPI. And that sort of gives you interfaces where you can add function calls in your code, and you can take measurements of various things. So you can, flops, whether or not they're SIMD instructions, whether or not they're fuse, multiply, adds, and the number of cache hits and misses for, the various levels of cache. And this would just be sort of very simple, right? Average time for a memory access, a load, and then the time for our flops. So number of flops and the average time to perform one. Okay, and right, because of our memory hierarchy, the average time for load and stores can vary considerably. But let's go ahead, come back to our matrix multiplication, and look at just one of our matrix sizes here. So we're looking at 2048, and we're just, the easiest thing to measure is time. Let's measure the time and the various speed up. So our naive one we'll use as the baseline. Expert one is, almost 130. OpenBLOS is, about twice that. Taco, a factor of 10 is respectable. And then halide, factor of 30. And if you're the expert in halide, significantly higher fraction. Okay, so is the speed up coming from reducing memory traffic? Well, we can measure the L1 data cache loads and stores, again, normalize them and look at what we've done. And we can say yes, but that's not the whole story, right? So our expert one, we're down to like 3% of the memory traffic. OpenBLAS is 2.3%, that's pretty good. Taco only gave us 50%. Then the halide, so the auto did pretty well, less than what we did with our expert. And then the expert did even less. But even though this is less than ours, right, this isn't the whole story. We can go from 3% or 2.6%, basically 3%, and still vary considerably in our speed up. So something else is going on. And it's the fact that each load and store, is not equal cost. If you incur a miss at one of the levels of the memory hierarchy, then that load or store takes longer than others. And so we can look and try to make sense of, well, what's going on here? And our performance model would change like this. You can just add terms in here for the cache misses in the other levels of the memory hierarchy. And this you can represent this pretty well insofar as these values. Okay, yeah, so, OpenBLAS, pretty high miss rate on the L1, but very, very low on the L2. And you can kind of see that maybe misses on the L2 seem to be part of that, maybe the primary indicator. That's a bit heuristic. And there's still more going on here. So, Taco, again, wasn't producing any SIMD instructions, whereas, our expert, or both halide gave us SIMD for 512-bit. Our naive one did not. And our expert one was only giving us 256 here. We've since modified it to give us 512, but I don't have a consistent measurement. But that's fine. Okay. So bottom line is, yes, the types of things we did to optimize like a naive implementation to something like expert, right? We're saying that's one path to producing a high performance bit of code. These are other ones using existing pieces of research, and we're trying to hit this upper bound. And so we can get about halfway there. Right. And, returning now to our high level view of a synthesis solution, I think there's two stages to this. First is to, start with the algorithm that has the lowest asymptotic complexity in terms of the number of operations. Generally, I think we can feel good about the notion that if we're reducing the number of operations, we should also be reducing the amount of data that we move or are required to move. But this is an important piece, and for now, this is what we've been trying to I'll say systematize again. Try to take what we know how to do by hand and put that in a general way in some other tool. Okay, and so to just summarize here, right? Minimizing communication is an effective strategy to achieve better performance. This principle should generalize well to distributed parallel algorithms in GPUs. I just showed it here for a serial CPU, but I believe there's enough out there in the literature to show that this is also true. There's already data and papers that exist to show that this statement is true. Right, and more or less, this is where we are. And part of the idea is scheduling, right? Changing the order of operations. But you have to do that with pretty good knowledge of the memory hierarchy and make sure you're exploiting SIMD. And then, matrix multiplication is a very, very low level kernel. What we want for a broader base of numerical linear algebra are lots of other things. And we've been looking at some other things. I just chose not to talk about them here in the interest of time. Okay.
Hi, so you mentioned that you wanted to do these different things, and one of them is look at better algorithms. So obviously, for matrix multiplication, there's Strassman's is much faster, and Strassman's is much faster on the big machines. Demo did all that.
Yep.
Yeah, so is there an automated way to start trying to find faster algorithms? Should they be somehow categorized some way that people can find them and use the piece?
In short, I would say I don't know. I'm not plugged in enough to the broader sort of computing side, electrical engineering side, and computer science side of the community that would, I think, produce those papers. But at the very least, yeah, I think you can start with just, as I mentioned, I'm going to go all the way back. We do kind of have a finite set of things here, right? So we can look over in our algorithm like, oh, here's a matrix multiplication, here's a matrix vector multiplication. These are the references where those high quality implementations are. That's a starting place for sure.
Well, I mean, like I teach
Yeah.
algorithms and so on. And so I teach them, like, here's an algorithm, but here's a faster one in parallel. In fact, I just did that today.
Yeah.
AKS sort versus Bitonic sort. Yeah, so it seems like though that there's no good way of doing that. I once actually sped up somebody's program a millionfold when I was a graduate student from a numerical analyst, but that's because I found out that, wait, Gauss did this. I couldn't claim credit for something Gauss did. And so there's no good way of finding these algorithms and linking them into this stuff. It's my problem.
Okay, yeah, right. So, yeah, I think I'm not aware of anything that does that automatically, but I think I understand the point you're making is that oftentimes if we make a mistake and we're naive, it's because we haven't had time to learn that there's a better solution sitting out there. Yeah. So I want to shorten that. Yes.
So if you look at the history of the commits of all these libraries, right, there's a huge amount of experimentation that goes on for each and every one of those commits, right? And it's an iterative process. The naive programmer gets it started, another guy or gal kind of looks at, oh, what if I do this? What if I do that, right? How can you get that sort of flow into this, what you're trying to achieve here?
Yeah, again, I don't know. Xin Yu is the program synthesis expert. He's not here, but I've heard him say that, like, okay, if we can explain, some of these things, then he knows how to do the synthesis. He seems very confident in that. I guess, it's that middle part's a mystery to me still. And I would say at least how you extract that from commits. I don't know if you necessarily want to look there. I guess I'm aware of another paper where this community that does program synthesis talks about lifting, where you sort of analyze your code and then lift the features off into what you should be doing. Yeah. Perfect. Yeah, no, you.
I get to ask questions in the panels. But, so how does some of the numbers that you said, that you showed translate to GPUs? That's the first part of the question. The second part is, even when we do simple operations in GPUs, more recent ones, it's taken behind the screen and all kinds of optimizations happen. Right? They even do, there's some random half precision additions that are happening even though you're not specifying anything. So in that context, is it even possible to do this kind of optimization when a majority of the work is done, is not exposed to us in GPUs?
Yeah, this is also, I think, a good question, right? So, if you've worked with NVIDIA GPUs enough, they try to keep a lot of details hidden from the programmers. That's like their business. They don't want that information getting out. And their libraries are pretty performant on their hardware, and you're probably not going to be able to do better. Yeah. So in that sense, I didn't show it here, but the communication avoiding LU and QR, elements, you can think of it as like composition of kernels into bigger algorithms, and there can be sort of larger optimization space across the algorithm. But with some of our, like the communication avoiding LU, you know, you use like just calls to BLOS. So you just compose the communication avoiding version with some library calls because those are available to you and you can't see behind them. Okay.
Thank you very much.
Yeah.